Dear students, today we will be discussing about collector efficiency factor and collector heat removal factor of a flat plate collector. See, now we know how to develop an energy balance equation. So, with the previous experience, we can write straight away what is the energy balance equation at the absorber plate. Okay? And also this S is nothing but the flux which is received by the absorber plate, which can be expressed by using this expression. Okay? So, S is equal to tau into alpha average into IT. Okay? So, earlier we had this S is a function of many parameters. So, we can simplify it by introducing this term tau alpha average and IT. Okay? So, let us now consider a flat plate collector with two glass cover system. Okay? So, we have an absorber plate here, this is the absorber plate, and this is glass cover 1, this is glass cover 2, which is at temperature Tc1 for glass cover 1 and Tc2 for glass cover 2. Okay? And Ta is the ambient temperature. So, if we need to know the radiative exchange or say energy or heat transfer between two plates, if we need to understand the heat exchange between plate and glass cover 1, we have some expressions of something like this. Okay? And then in between this glass cover, we can use this expression to calculate the rate of heat exchange, and finally heat exchange from this glass cover 2 to ambient can be estimated by using this expression. So, if we see those expressions very precisely, what we can see in all the three expressions, there are two components. One component is for convective part and other component is for radiative part. Okay? All the three cases you can see this is convective part and this is radiative part. This is convective part, this is radiative part. Okay? So, if I am interested to draw thermal resistance of this two cover system, then this may be for convective part and this may be for radiative part. So, if we start from this absorber, so as we understand these two components, this is for convective part, this is for radiative part when heat exchange is taking place from this absorber plate to the glass cover 1. And then from glass cover 1 to glass cover 2, we have these two expression. Okay? And then from glass cover 2 to ambient, we will have these two expression. Okay? And then this part is towards the bottom. Okay? These are the resistances. So, finally, if I am interested to know the resistances between the plates, so we can draw this. Okay? This R1 is from glass cover 2 to ambient, and this R2 is from glass cover 1 to 2, and R3 is from absorber plate to glass cover 1. Okay? And this part is the bottom loss or bottom resistance part, right. So, if we combine all, then what we will get is a UL, right. So, this UL is nothing but UT plus UB plus US, which has already been demonstrated how these are connected and how this UT can be calculated. So, finally, what we will have, so this will be something like overall loss coefficient. So, finally, this will be an overall or say equivalent thermal network for an FPC, which is considered in this discussion, right. So, now let us understand the temperature profile. Okay? So, here what I mean to say, let us consider a collector of something like this, and let us consider two tubes are there. Okay? Just to have considered two tubes. Okay? And this may be y and this may be x direction, right. So, we are now interested to develop the temperature profile. So, how it will be? So, temperature will be something like this. Okay. So, this is the temperature profile. So, this will be the temperature, and we can extend it this in the x direction at a fixed value of y. Okay. So, this will be the temperature profile. So, what is showing here? So, above this or in the tubes, so here, so temperature will be constant and in between temperature variation will be there. Okay. It will reach a maximum and then it will reduces, okay, and then it will be uniform. And if I am interested to know along the flow direction, then what will be the temperature profile? Let us draw it. So, along the flow direction, so this may be T, okay, and this may be y and this may be x. Okay. So, here what I can draw, this temperature profile will be, this is T and then we have y and this will vary something like this. So, this will be at a fixed value of x. Okay. So, this is along the flow of the fluid and this temperature profile is in between the two tubes. Okay. So, these profiles are important while deriving the expression for collector efficiency factor. Okay. Now, let us understand how these QU are related with F dash, which is nothing but collector efficiency factor, and then Fr, which is nothing but collector heat removal factor. Okay. So, already we know this expression for useful heat gain, QU is equal to AP into S minus QL, which is nothing but the losses, right, and S is a function of many variables, but we can simplify. S is something like alpha tau average multiplied by I T. Okay. That also I can write, or we can very precisely we can use this expression, right, and QL is nothing but UL AP TP minus TA. Okay. So, if we know UT top loss coefficient, then bottom loss coefficient, then side loss coefficient, then we can calculate what is UL, and once we know UL, then we can calculate what is QL. So, once we know QL, on substitution here in this energy balance equation, we can calculate what will be the useful energy gain, okay, since we know this S value, right. Now, if we substitute this value and we simplify, then what we will get, QE is nothing but APS minus ULAP TPM minus TA. Okay. So, this expression, if we need to calculate this QU or useful heat gain, we must know this temperature. Okay. Ambient temperature is always known to us, but TPM it is very difficult to know this TPM. Okay. So, if we do not know this TPM, then what will be our next target to simplify this calculation with a known value of this temperature. Okay. So, what kind of temperature we can use it to simplify this equation, right. So, keeping this in mind, these two expressions are developed. This QE is equal to F dash of something, and then we will have TF, this is local fluid temperature, and this Hotel-Wheeler-Bliss equation, who has developed this expression for useful heat gain, is a function of TFI. Okay. Because this TFI is always known to us, inlet fluid temperature we can always measure before entry to the fluid in the tube. Okay. So, once we know this TFI, of course, straight away we can calculate what will be the QU if we know this other parameter, okay, UL and S. Okay. So, this F dash is nothing but collector efficiency factor, which is defined as the ratio of the actual useful heat collection rate to the useful heat collection rate which would occur if the collector absorber plate are at the temperature of TFI. Okay. So, this is the definition of collector efficiency factor, and its value ranges from 0.8 to 0.95. And how to define this FR? This collector heat removal factor is defined as the ratio of the actual useful heat collection rate to the useful heat collection rate which would occur if the collector absorber plate are at the temperature of TFI everywhere. Okay. So, this temperature should be TFI and here it will be TFI, which is local fluid temperature, and this TFI is nothing but inlet fluid temperature. Okay. And each value varies from 0 to 1. So, this FR can be expressed something like this. Okay. So, we will derive one by one how this average can be estimated, and then finally, how this FR can be estimated. Okay. So, now let us derive the expression for collector efficiency factor. So, we adopt the methodology of 1D analysis or one dimensional analysis. Okay. So, in the first approach is one dimensional flow of heat in the observer plate in a direction at right angles to the direction of the fluid flow is considered. Okay. And second consideration or second approach is the heat flow from the plate to the fluid across the tube wall. And third approach is one dimensional flow of fluid inside the tubes. Okay. So, let us consider this configuration. Okay. So, this is an observer plate of say thickness del p, right, and two tubes are considered in that collector, and let the pitch be W, and if we consider L2 is the width of the plate, then what we can say, this L2 is nothing but W into N. Okay. So, that we can do, and L1 be the length of the collector or length of the tube. Okay. And di is the internal diameter of the tube and d naught is the outer diameter of the tube. And as you can see, these are dashes line, these are nothing but the adhesive used to bond this tube here in the observer plate. Okay. So, let us concentrate with this small section here. Okay. And this is the x, okay, this is the x, and small section is dx in between these two tube. Okay. And we will apply the knowledge of heat transfer here. So, heat will be conducted from here and then some amount of solar radiation will be falling from the top, which will be transferred through this observer plate to this fluid. Okay. So, by taking a slice, this is dy, so dy will be something like this. Okay. This will be dy along the flow direction, and neglecting heat conduction in the plate in the direction, the energy balance for an element dx dy of the plate we can write the net heat conducted into the element. So, the heat conducted from this plate to this fluid, and the incident solar absorbed, the amount of energy which is absorbed here, which is nothing but the heat loss from the element. Okay. And here as you can see, this is a temperature profile what we have discussed before. Okay. So, in between the tubes variation of temperature will be there, but no, in the tube this temperature is not varying, it is a constant because heat is carried by the fluid. Okay. Again this will go something like this, again one more tube will come. Okay. So, this will vary along x direction. So, now if we write the same expression again, this net heat conducted into the element plus incident energy balance minus heat loss from the element is 0. Okay. So, what is the net heat conducted into the element? So, we can use this expression for conduction, and then amount of incident energy absorbed we can write S into dx into dy, this is area because we have considered this small segment. Okay. So, this is dx along this and then this is dy. Okay. So, it will be like a something like this, and this loss will be Tp. So, here we are using Tp instead of Tpm. Okay. Let us say plate temperature, we are not using m here, and Tp minus Ta multiplied by dx dy is the area, right. So, if we divide the entire expression by dx dy, so our expression will be something like this. Okay. And again we can simplify further. So, d square Tp by dx square will be something like this. Okay. Because UL by Kp dp, and then if we take UL outside, then this will be free from UL minus S by UL. Okay. Now, there are boundary conditions. So, what are boundary conditions? At x is equal to 0, dP by dx is 0. Okay. So, as you can see here, if we consider, if we go back here, if x is 0, maybe here at this point x is 0. So, this is the peak. So, this is no gradient will be 0 here. Okay. That is why dP by dx is 0. So, this is the boundary condition 1, and at x w minus d naught by 2 at Tp is equal to Tp naught. Okay. So, that also you can see, this is w, so this part is d naught by 2, and also this part is d naught by 2. Okay. D naught by 2. So, w minus d, so this when d naught by 2 plus d naught by 2, it will be d. So, w minus d. Okay. So, w minus d divided by 2. Okay. So, that means this is the one. Okay. So, at Tp is equal to Tpo, right. So, now we will define a term called m, which is nothing but square root of UL by Kdp, and maybe one term xi is Tp minus Ta minus S by UL. Okay. So, if we use this terminology in this expression, then it will be something like dou square xi by dou x square is equal to m square xi. Okay. So, this will be simplified like this, and accordingly we have to modify these boundary conditions. So, at x is equal to 0, the xi by dx is equal to 0, and at x is equal to w minus d naught by 2, xi will be Tpo minus Ta minus S by UL. Okay. So, if we solve it, then we will get the general equation something like this, and it is a hyperbolic function, right. So, now let us solve this expression, because this will be the yield of the solution. Before we come to this stage, so we need to do something in between. Let us solve it. So, we know the xi, and then we can write or d xi by dx is equal to C1 m, this will be cos of hyperbolic mx plus C2 m sine of hyperbolic mx. Okay. So, we can use the boundary condition here. So, x is equal to 0, then d xi or d I can write, it is one dimensional. So, this will be 0. So, C1 m cos 0 1. So, C1 m is plus C2 m multiplied by sin 0 0. Okay, it will be 0. So, C1 will be 0, right. So, again we know the first equation. So, we need to find out the C2 value. So, how to calculate the C2 value? So, Tpo minus Ta minus S by UL is equal to, so C1 is 0, that expression we can know C1 sine of Hmx, because C1 is 0, that part will be 0, then plus C2 cos of H, because when we use the second boundary condition, so at x equal to w minus d naught by 2. Okay. So, t will be, we can go back to that, understand, this is the boundary condition, this xi will be Tpo minus Ta minus UL. Okay. So, that way we can use this. So, this is nothing but no xi part. Okay. So, this is first boundary condition, and here Hm w minus d naught by 2, right. So, once we simplify it, then what we will get, C2 will be Tpo minus Ta minus S by UL. Okay. And this will be divided by cos of Hm w minus d naught divided by 2. Okay. So, if we substitute this value in that expression for xi, this, okay, what we will get is the general solution. Okay. So, just one step I will do here. So, this will be xi is equal to T p minus T a minus S by U L is equal to, so C 2 is something like this, T p o minus T a minus S by U L, okay, divided by cos of H m W minus D naught by 2, right. So, multiplied by cos of H m x, right. So, if we divide this expression, the entire expression by this T p o minus T a minus S by U L, then what we will get is the yield of the solution. So, this will be something like this, T p minus T a. So, we can just modify the expression. So, this will be something like this. So, once we are done with this solution, next phase is to calculate the rate at which energy is conducted through the plate to both the side of the tube, okay. Because see, we have considered this slab, okay, and then we have the tubes, what is considered was here. So, when we are considering this, so from this side also heat will be conducted to this tube, okay, right. We are considering heat is coming from this side, also we need to consider heat will come from this side, because it is a nearing tube, okay. So, one more tube will be here, so temperature profile will be here. So, heat will be conducted from both the side to this tube. So, that is why we need to multiply this expression by 2 Kp del P T p by dx at x is equal to W minus D naught divided by 2, right. So, if we need to differentiate this T p, then again we have to use this expression, okay. So, what happens, this dTp by dx we can do here. So, this dTp by dx at x is equal to W minus D naught divided by 2. So, what will be the expression for this? We can straightway use this expression and we can do it, okay. If we use this here, okay, then it will be something like T p o minus T a minus S by U L. So, m will come out here, okay, and then it will be sine of H m W minus D naught by 2 divided by cos of H m W minus D naught by 2, okay. So, this will give a value of something like U L by K p del P half, and then we have T p o minus T a minus S by U L is equal to tan of H m W minus D naught by 2, okay. So, now you can simplify it, since you know this, and then already K p d p is multiplied here, okay. So, we can simplify it, and then finally what we will have, this 2 K p d p by U L square root will come here, and then other expression will be same as this expression, right. Now, the rate at which energy is absorbed just above the tube also we know, okay. So, D naught is the outer diameter of the tube, and this expression is known to us, okay. So, we can straightway use it for calculation of rate at which energy is absorbed in the tube, okay, just above the tube. So, if we add these two expression, this equation B expression and then equation A expression. So, what we will have, then dq is equal to n multiplied by this expression, okay. So, this is common. So, I have skipped one step here. So, since this part is common, so we can take it out, okay, and we can now introduce these two part in the bracket, right. So, also this plate effectiveness is defined as the ratio of the heat conducted through the plate to the fluid tube, okay, to the heat which would have been conducted if the thermal conductivity of the plate material was infinite. Okay. So, under that consideration we can define this effectiveness. Okay. So, effectiveness will be something like 10 hyperbolic m w minus d naught by 2 to m multiplied by w minus d naught by 2. Okay. So, this can be utilized in this expression C, and then we can modify this expression something like this. Okay. So, this expression is in terms of plate effectiveness phi. Okay. So, phi is multiplied here. Now, next step is to calculate the flow of heat from the plate to the fluid. So, when we are talking about flow of heat from the plate to the tube, then we must consider 3 thermal resistances, because heat will be lost. Okay. So, why this heat loss will be there? So, these thermal resistances need to be considered. So, what are those? The adhesive used for attaching the tube to the absorber plate, okay. Then tube wall, okay. As you can see, these are the adhesive used here in this expression. This is the plate, and then this is the tube wall, okay. And then heat transfer coefficient at the inner surface of the tube. So, this is your inner surface of the tube, okay. So, these resistances are offered, okay. So, this can be represented by this resistance line, okay. So, since the material of construction of this tube is copper, so it offers very less resistance to the heat flows. So, because of that, this is not considered in the present derivation, okay. So, if we do not consider this and only these two are considered, then our expression will be something like this: 1 by n dq u by dy is something like TPO minus TO to these two resistances. Okay. One is for the adhesive used, and then second one is for the heat transfer coefficient at the inner surface of the tube. Okay. This delta is the average thickness of the adhesive, and K is the thermal conductivity of the adhesive material, and Tf is the local fluid temperature, and Hf is the heat transfer coefficient on the inside surface of the tube. Okay. So, now we can use these equations, and then we can arrive at an expression of something like this. Okay. So, here what we did, by using this equation D and E, we tried to remove this TPO, okay, and final expression will be something like this. Okay. Now, we can define this collector efficiency factor F dash is nothing but this. Okay. So, which is nothing but ratio of the actual useful heat gain rate per tube per unit length to the gain which should occur if the collector absorber plate were all at the temperature of Tf. Okay. So, now again we can simplify, and we can have this equation, no, this F dash we can use in equation F, then this will be a very simple equation: 1 by n dq u by dy is W multiplied by F dash in bracket S minus UL multiplied by Tf minus Ta. Okay. Now, once you know this, then from that we can calculate what will be the useful heat gain. Qu is equal to F dash multiplied by this expression. Okay. Now, let us see what happens if the configuration changes. Okay. So, this expression is for the tube bonded above the absorber plate. So, you can see the cases what we have derived just now, that was for the tube which is attached below this absorber plate. Now, if you see the case when these tubes are attached above the absorber plate, then expression will be something like this. Okay. And sometimes these inline configurations are also used in absorber plate. So, this is the absorber plate, and the same line will have these tubes. Okay. So, if this is the case, then we need to use the expression for F dash something like this. Okay. So, straight away you can use those expression for calculation of collector efficiency factor for these two configurations. Okay. Now, come to the analysis part for collector heat removal factor. So, in this case also one dimensional analysis along the direction of the flow will be considered. Okay. So, objective is to determine the variation of fluid temperature along the direction of fluid flow. Okay. As we have discussed the temperature variation, so it goes something like this. So, this is an inlet of the fluid and this TFO is the outlet of the fluid, okay, temperature. So, it varies something like this. Okay. At the outlet, of course, we will get the highest temperature, right. So, this is the variation of fluid temperature in the flow direction, right. So, if we consider a small control volume here, okay, this is a control volume. So, dy is the thickness, right, and if we apply the first law of thermodynamics, that is the rate of change of enthalpy of the fluid flowing through the control volume is equal to the rate of heat transfer to the fluid inside the control volume. Okay. So, if we use this first law of thermodynamics, then it will be something like this, because we know Q is equal to m Cp dt. Okay. Since we are dealing with the n number of tubes which is attached in a flat plate collector, because of that n has to be considered here. Okay. And this Q we represent in terms of Tf. So, our expression will be something like this. Okay. So, we can write dTf by dy will be something like this, right. Now, we can derive the expression. So, we can write dTf by dy minus Wf dash ul by m by n into Cp, then we have S by ul plus Ta, okay, it's minus Tf, right. So, this will be equal to 0. Maybe we can write this expression, maybe star I will write, right. So, now let us consider, say theta f is something like S by ul plus Ta minus Tf, okay, and P is equal to Wf dash ul by m dot by n multiplied by Cp, right. Now, if I will differentiate it, T theta f by dy, then what we will have, these are constants. So, this will be minus dTf by dy, right. So, if we use the expression star here, I have not yet mentioned the boundary conditions, we will use it. So, it will be something like, so boundary condition was, so when y is equal to 0, okay, then Tf is equal to Tfi, which is obvious, okay, this is obvious. So, if we modify this boundary condition, if y is equal to 0, then we have theta f will be theta fi, okay. So, here, so equation star implies what you can write is something like minus d theta f by dy is equal to, this part is p and again this part is theta f is equal to 0. Okay. So, again what we can write, if we multiply both sides with minus 1, so d theta f is dy, then you have plus, right, this f is equal to 0, or what we can write d theta f by f is equal to minus p into dy, and if we integrate what we will get, ln of theta f is equal to minus p into y plus c, right. So, this is an differential equation, okay. So, this is a solution of this. So, on integration what we will have, ln of theta f is equal to minus p into y plus c, okay. Now, apply the boundary conditions. by applying BCs, what will happen? So, at y is equal to 0, this equation you need to use. At y is equal to 0, theta f is equal to theta f I. Okay. So, ln of theta f I is y is 0 means this expression will be 0. Okay. So, C will be theta f I. Okay. This maybe you can write double star. So, now using this in double star equation, this star. So, ln of theta f is equal to minus p into y plus ln of theta f I. Okay. So, if we know deduct theta f I from both the sides, then it will be something like this, minus p into y, which implies ln of theta f by theta f I is equal to minus p into y, and it will be something like theta f is equal to theta f I exponential of minus p into y. Okay. So, we can substitute those values p and theta here. Okay. So, if we substitute this, then theta f is equal to s by u l plus T A minus T F is equal to, so theta f I is how much? It will be s by u l plus T A minus T F I. Okay. And then e to the power of p will be minus w f this u l by m by n into C p into y. So, this minus is here. Okay. So, our expression will be something like this, right. So, now move to the next slide. So, if we divide both the expression by s minus u l plus T A minus T F I, then what we will have? This divided by this will be this part. Okay. So, that is how we will show here. So, this will be something like this, right. So, this fluid outlet temperature. Okay. So, one more thing I missed here. So, here as I know N into W is L2, okay. So, which is applied here. Okay. This is applied here. Okay. If you go back, so you can see W N is at the bottom side, and then if you multiply by W into N is something like L2. Okay. That is how we can write L2 here. Okay. Now, the fluid outlet temperature TFO at y is equal to L1. So, because length of the tube is L1. Okay. So, TF is equal to TFO, that is obvious. So, tube is here. Okay. This is the, so y it was 0, and when it was y is equal to L1. Okay. So, this is nothing but this is TFI, this is TFO, right. So, that is how we can write this expression something like this. Okay. So, this will be at here at the outlet. Okay. And if it is at the outlet, then y will vary from 0 to L1. Okay. So, that is how it is L1 here. Okay. Now, if we deduct this expression from both sides, so this will be something like this. So, we will have this kind of expression. Okay. TFO minus TFI divided by this expression is equal to 1 minus exponential of that considered P, right. Now, what we are interested about, this useful heat gain, right. So, this useful heat gain rate for the collector is something like this mCp dt. Okay. So, if some amount of mass is flowing inside this tube and Cp specific heat of fluid is known, and then these two temperature, inlet and outlet temperature is known, then straight away we can calculate the useful heat gain rate for the collector, right. So, delta T. So, we can modify this expression because this is known to us now. Okay. So, if we know this multiplied by this, then we will have this expression, right. So, now what we can see here, this QE is in terms of TFI, okay. Only we need that inlet fluid temperature, okay. So, once you know this inlet fluid temperature and other expression, then straight away you can calculate what is QU, which is much easier than calculating QU in terms of mean plate temperature TPM, okay. So, this QU is equal to FR AP of something like this, okay. So, what is FR now? FR can be expressed something like this, okay. So, this FR is nothing but collector heat removal factor, okay, which is very important parameter for performance of a flat plate collector, okay. Also, this is an important design parameter since it is a measure of the thermal resistance encountered by the absorbed solar radiation in reaching the collector fluid, okay. So, why it is important you understood now. And finally, what expression we get is something like QU is equal to FR AP, then multiplied by this S minus UL TFI minus TA, okay. So, QU is related with TFI, and this is a famous equation developed by Hotel Wheeler and Bliss, okay, and this expression also known as Hotel Wheeler Bliss equation, okay. Now, if we summarize about collector efficiency factor, it goes something like this. We have learned this how to calculate QU, and also we can calculate instantaneous thermal efficiency, okay. So, this expression will be something like this if we express in terms of F dash. So, this collector efficiency factor F dash is essentially a constant for any collector design and fluid flow rate, okay. This collector efficiency factor decreases with an increase in the center to center distance of the tube and increases with an increase in the material thickness and thermal conductivity, okay. An increase of overall loss coefficient decreases F dash, okay, whereas an increase in the fluid to tube heat transfer coefficient increases F dash, okay. So, these are very important observations. So, we should keep in mind why actually F dash is very important as far as design of a flat plate collector is concerned. So, if we summarize about collector heat removal factor, so already we have defined how this FR can be calculated and which is the ratio of the rate of actual useful energy gain to the rate of useful energy gain if the entire collector were at the fluid inlet temperature in a forced circulation mode, okay. So, this is the expression for FR, and also sometimes you can define a term called flat plate flow factor, okay. So, this is something like FR by F dash, okay. So, this is the expression for flat plate flow factor, okay. So, if we plot the variation of F dash with respect to this expression, so we can get this kind of plot, okay. So, this is also important sometimes to know the variation of this flat plate flow factor with respect to this flow rate factor, okay. Also, instantaneous efficiency is important. So, at any moment if we need to know the efficiency of the collector, we can straightway use this expression once you know this tau alpha value and this overall loss coefficient, okay. So, this is known to us now, and this overall collection of thermal efficiency is defined as the ratio of useful gain to the incident solar energy over the same period of time. So, if I have to calculate this collector efficiency, so we can integrate over time and we can calculate it, right. So, this is for useful heat gain and this is for the amount of solar radiation received at a particular site. So, straight away you can calculate the collector efficiency. So, this expression is for instantaneous and this is for time based efficiency, okay, or collector efficiency, or you can say. So, we can solve one problem, okay. So, this problem goes something like a FPC has an aluminum absorber plate having thermal conductivity 211 watt meter square degree Celsius of thickness 0.35 mm and an area of 1.5 meter square, and it has two riser tubes. So, two tubes are there. Okay. So, two tubes are there and diameter is given, okay, and length of the tube is also given. This length is given, it is 1 meter. Okay. Determine the collector efficiency factor F dash for this collector if the convective heat transfer coefficient from the inner tube surface to the outer is 50, 100 and 500 watt per meter square per degree Celsius. Okay. And overall heat transfer coefficient is given as 7.2 watt meter square per degree Celsius. Okay. We know the expression for M, then plate effectiveness, okay, and F dash or collector efficiency factor. Okay. So, once we substitute those values, so we will get this kind of values. So, once this heat transfer coefficient changes, you can see the change in F dash values. Okay. So, if we can increase this F dash value, of course, we can get the higher useful heat gain. Okay. So, maybe we can solve one more problem. So, it goes something like this: a flat plate collector which tube inline with the absorber plate. So, this configuration will be something like if you have this kind of configurations. Okay. So, it goes something like this, it is inline. Okay. Fluids are flowing in this channel. Okay. So, overall loss coefficient is given as 5.8. So, this UL is something like 5.8 watt meter square Kelvin. The inner and outer diameter of the tubes are given. So, D naught is given as 14 mm, DI, and its D naught is 18 mm. Okay. And center to center distance, this is W is 12 centimeter. Fluid to tube heat transfer coefficient is given as 205. So, HF is given as 205 watt meter square Kelvin. So, we are interested to calculate collector efficiency factor, that is F dash for the configuration of something like tube inline. Okay. And absorber plate material, two different materials are to be used. So, in the first case is copper having thickness 0.2 mm, and second case absorber material is galvanized iron and thickness is 1.3 mm. Okay. And thermal conductivities of these two materials are given. Okay. So, let us start with this expression F dash. We know the expression 1 by WUL, then we have 1 by UL, then W minus D naught into phi plus D naught, okay, and then we have 1 by pi di HF. Okay. And also we know the expression for phi. So, this phi is something like 10 hyperbolic m W minus D naught by 2 divided by m W minus D naught by 2, right. So, these values are known to us. So, straight away you can calculate what is phi. Before that we must know what is m. So, m is equal to root over UL by Kp del P, right. So, if we substitute the values of UL is 5.8, then what is Kp? Kp is, so if we consider copper, so in the first case Kp is 350 and del P is 0.2 into 10 to the power of minus 3. Okay. So, this thickness is del P. Okay. So, on substitution, what will be the value of m? It will be 9.10. Okay, this is the value. So this will be in 1 by meter, right. So if we use this m here, so let us write 10h, this will be 9.1, then w is how much, is 12 centimeter. So this will be in meter 0.12, and d naught is 18 mm. So this is 0.018. Okay. So this divided by 2, and this will be m is 9.10, then you have 0.12 minus 0.018 divided by 2. So this gives a value of 0.93389. Okay. So if we use this phi here and then substitute all those values, so here straight away you can substitute those values. So 1 by w value is, we have 0.12 into UL is 5.8. Okay. Then we will have 1 by UL is again 5.8, then you have, I will use this, then W is how much, 0.12 minus D naught is 0.018, then phi how much we got already, 0.93389. Okay. Then we will have D naught. What is the value of D naught here? 0.018. Okay. Then plus 1 by pi di is 0.014 into HF is 205. Okay. So this gives a value of 0.880. Okay. So if we change the value of this thickness 1.2 and material is galvanized iron, and conductivity will change, it will be 35. So what value we will get is about 0.856 as per my calculation. Okay. So you can see this one is always better than 856. Okay. So always we will go for this copper based absorber plate. Okay. So that is how the kind of material to be used for a particular applications will be decided by those calculations. Okay. So once we know these F dash values, then we can decide so which one will be the best for the particular application, right. So that is what it is demonstrated in this example. Also sometimes transient analysis is important, because we need to know what is happening with time. Okay. How much time it will take to get an uniform temperature of the absorber plate. Okay. So this kind of expressions can be generated for transient analysis. Okay. So this expression can be used either to find the time taken by the collector to reach the mean plate temperature corresponding to the prescribed fluid inlet temperature, or to determine the mean plate temperature after a certain amount of time has been elapsed. So straight away you can use this equation for those two conditions. Okay. And this slide shows the specifications of a commercial flat plate collector. So all the informations are here. As you can see, like overall collector area, aperture area, absorber area, weight capacity, then the solar glass transmission, then solar radiation absorption, solar radiation emission, then efficiency and efficiency coefficient, okay, maximum operating pressure, stagnation temperature, and then material and construction, the kind of material, absorber sheet, what are the material, it is aluminum, absorber plate coating. So what kind of coating, it is a selective coating, we will discuss those selective coating maybe in the next class. Then absorber tube, what kind of tube material used as a absorber tube. Then frame, glazing, all the informations we must know when we go for purchase of this kind of solar flat plate collector for maybe commercial purpose or maybe for research purpose. Okay. So, I hope that by now you understand the importance of those terminologies what we have discussed. Okay. So, as a layman all people knows about this, but no technicality you must know how these are connected with commercial aspects. Okay. Now, we will learn something about combination of flat plate collectors. Okay. There might be some cases when we need to connect the flat plate collectors in series or maybe in parallel or maybe both, means series and parallel. Okay. So, in case of parallel connections, the upper and lower headers of each FPC are connected to increase the volume of the water to be heated. Okay. The mass flow rate per FPC is the total mass flow rate divided by the number of FPCs. The outlet temperature or outlet water temperature is the same as the outlet of each FPCs, because these are connected in parallel. Okay. These are connected in parallel and these are the headers. Okay. These are the headers. So, this may be one temperature. Okay. So, inlet and outlet. So, outlet temperature will be same, this outlet temperature will be same, this temperature will be same for all the collectors when it is connected in parallel. Okay. So, these FPC modules can operate in natural as well as force mode. Okay. This may be thermosiphonic, okay, because of this density difference, mass movement of the fluid will be there as temperature increases. Okay. That is called natural, or if some kind of pumps and other devices are used, that becomes forced. Okay. So, for series connection what happens, this is the collector 1, this may be collector 2. So, it may be inlet, this is outlet. So, outlet will be connected to inlet here, and then this outlet will go to the other collector. Okay. So, other collector here as a inlet. Okay. So, that way we can maximize the temperature. Okay. So, here we can maximize the volume and here we can maximize the temperature. Okay. So, volume of water and this temperature of the water, if water is a heat transfer fluid. Okay. So, this outlet of one row of FPC is connected with the inlet to the second row of the FPC. Okay. And that continues as per the requirement. The mass flow rates are the same for all the rows. Okay. The outlet temperature depends on the number of rows of FPCs connected in series. Okay. So, this temperature is depends the number of this kind of FPCs are connected in series. Okay. So, such series connected FPC modules can only operate in the force mode. So, here thermosiphonic mode will not work. So, we need to apply some kind of active devices like pumps, and of course, we will have some other configurations like mixed connection combination. Okay. So, the first FPCs are connected in parallel for a given capacity of the hot water to make one row, and such modules formed are connected in series to increase the temperature as per the requirement. Okay. So, this is generally referred to as arrays, right. So, we know the arrays for PV systems, then we can also define similar kind of configurations here in case of flat plate collectors. Okay. So, these FPCs arrays will only operate in the force mode. Okay. We need to apply some kind of active devices. So, here we can see the parallel connections. So, this FPC 1, 2, 3, 4, 5, these are connected in parallel. Okay. So, this is a header and this is one more header, this is for inlet, this is for outlet. Okay. So, these temperatures are same for all the collectors. Okay. But we can maximize the volume of water to be heated or required for particular application. And in case of mixed connections, we will have this kind of configurations. These tubes are connected in parallel, again these are connected in series. Okay. These three are connected in parallel and then these are connected in parallel, but no, these sets, this one and this one are connected in series. Okay. So, in order to get the desired temperature and mass flow rate, right. So, this kind of configurations are really applicable in community places like maybe hostels or maybe in apartments. So, let us summarize what we have discussed today. We discussed energy balance of an observer plate, then thermal resistance network, then temperature profile of a FPC. So, what happens in the x direction and y direction. Okay. So, if we consider two tubes, its variation will be something like, it varies, then it will be something like this. Okay. So, here heat is carried by the fluid. So, there is no rise in temperature, but in between this rise will be there, and also we have studied how heat is conducted to this tube through conduction as well as the amount of heat received from the solar flux. So, we have analyzed the collector efficiency factor as well as collector heat removal factor, and also we have understood the importance of these two factors in designing flat plate collector, and also we have studied instantaneous efficiency and collector efficiency, and also we have studied the series and parallel connection of collectors and what condition we can use series connection and what condition we can use it as a parallel connection. Of course, we can combine both as per the requirement of amount of volume of water required and particular temperature required. So, thank you very much for watching this video. Thank you.